Alright, so in the last section we talked about what the graphs of sine and cosine look like. In this section we're going to be talking about what the graphs of tangent, cotangent, secant, and cosecant look like. First, let's talk about tangent. So tangent looks like this. This is f of x equals tangent of x. So the tangent graph has a domain of all real numbers except the only numbers that aren't allowed to go into this function are odd multiples of pi over 2. So I'm going to write odd multiples of pi over 2. So what does that mean? That means 1 pi over 2, that means 3 pi over 2, that means 7 pi over 2, that means 5001 pi over 2. None of those are allowed to go into this function. They're not defined on this function, and you can see that from the graph. You can see where that asymptote is there. You're not allowed to put anything in for odd multiples of pi over 2. The range, however, is all real numbers. So the range of the tangent graph is all real numbers. It's continuous on its domain. So that means that any number we're allowed to put in, it is continuous on. It's symmetric about the origin. So that means, remember, if you rotated your entire graph, let's see if I can do it on, I don't think it's going to let me do it on here. If I did this, it would look exactly the same. That means it's symmetric about the origin. We also have some vertical asymptotes, an infinite number of vertical asymptotes at x equals k pi over 2. So this is the same thing as the domain. We have asymptotes where our domain is not defined. K is an odd number here. So just like we did before, 3 pi over 2, 7 pi over 2, 5001 over 2. Has vertical asymptotes at all of those. For end behavior, there is none. And the reason is because the function oscillates between negative infinity and positive infinity. So sort of opposite of sine and cosine, they oscillated between negative 1 and positive 1. This oscillates between negative infinity and positive infinity. But why do we have vertical asymptotes? Well, that's because tangent can actually be written as tangent of x, can be written as sine of x over cosine of x. So wherever cosine is 0 is where tangent is undefined. So tangent has a denominator that may be 0, which makes the function undefined. So cosine could be 0, which is why the function is undefined when cosine is 0. And this happens infinitely many times. Let's look at a picture. So this is our tangent graph. The green is tangent. I tried to trace it a little bit there, but you can see it occurs a bunch of times in this picture. Tangent has asymptotes at the zeros of cosine. Tangent has asymptotes at the zeros of cosine and zeros at the zeros of sine. So what does that mean? That means that at the tangent has asymptotes at the zeros of cosine. Cosine is in blue here. So let's see, the 0 is here, 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 here. And you can see that there's an asymptote there, there, oops, there, there. Those are our asymptotes of tangent. It also says that tangent has zeros at the zeros of sine. So we can see that too. Where sine is 0, tangent 0. Where sine is 0, tangent is 0. Let's talk about cotangent. Cotangent is the reciprocal of tangent. So that means that cotangent of x is equal to cosine of x over sine of x. So it's the reciprocal. Remember, tangent was the other way, cotangent is this way. And cotangent, this is a little bit confusing to look at first, but we'll go through it slowly. Cotangent has asymptotes at the zeros of sine and zeros at the zeros of cosine, so opposite. This is your orange is cotangent, which is what we're talking about. You can see that wherever sine is, so let's find the sine graph, it's blue. Sine is blue here. So wherever sine is, wherever sine has a zero, here, here, and here, we have asymptotes for cotangent. And then the zeros of cosine, so cosine's in red, 0 here, 0 here, 0 here, that's all where cotangent has its own zeros as well. So again, they're just opposite of each other. Important to remember them properly. This is the graph of secant. And secant is the reciprocal of cosine. So there's a couple of things that are true about this graph. And I'm not going to write them all down, but if you want to, that works too. So when cosine is in green, and secant is in blue. When cosine is equal to 1, secant is equal to 1. Cosine equal 1, secant 1. Cosine 1, secant 1. Secant also has asymptotes at the zeros of cosine. So where is cosine 0? Here, and here, and here, and here. And you can see that there's asymptotes there. There's asymptotes at the zeros of cosine. The maximums of cosine, so maximum here, here, and here, are the minimums of secant, and the minimums of cosine, here, here, and here, are the maximums of secant. So that graph was secant, this is the graph of cosecant. And cosecant is the reciprocal of sine. So when sine is equal to 1, cosecant is 1. Sine equals 1, cosecant 1. Sine is 1, cosecant's 1. Cosecant has asymptotes at the zeros of sine. So here, here, here. You could see that if I extended those lines, they would be asymptotes. And sort of the same thing, secant and cosecant have this in common. The maximum of sine is the minimum of cosecant, and the minimum of sine is the maximum of cosecant. Pretty easy. So now we're going to be solving some trig equations. We want to find the smallest positive number x, such that x squared is equal to cosecant of x. How do you do this? Well, you need to graph both of these on your calculator. So under y1, you'll set that equal to x squared, and under y2, you'll set that equal to cosecant of x. And then when you get a graph, we know that cosecant looks something like this. And those are going down, and those are going up. And then you know that x squared looks something like that. So in order to solve the equation, the smallest positive number is going to be whatever that number is right there. And you can do this on your calculator. Second, calculate intersect, and you get x is approximately equal to 1.068. And we're going to be doing a couple more examples of this in class, and that's it for this section.